Imagine waking up one morning. Everything seems normal at first. The sun rises in the east, just as it always has. You make your coffee. You glance at the news. But then, you notice the first small sign that something is profoundly wrong with the world. A hiker pulls out their compass, only to see the needle spin wildly. Useless. A sailor, far from shore, finds their navigational equipment has gone haywire, pointing to a phantom north that isn't there. These aren't isolated incidents. All over the globe, one of humanity's oldest and most reliable tools for finding our way has suddenly become a relic, a toy, with no purpose. This is just the beginning of a silent, global catastrophe. The strangeness doesn't stop with our technology. As twilight descends, the sky puts on a show of terrifying beauty. The familiar, delicate dance of the aurora borealis, usually confined to the high polar latitudes, explodes across the entire planet. Brilliant, shimmering curtains of green, pink, violet. Light drape themselves over the skies of New York, Cairo, Tokyo. People watch in awe and growing fear. This isn't a celestial celebration. It's a warning. The protective bubble that has enveloped our world for eons has just popped. The sky is no longer a safe boundary. It has become a window, wide open to the dangers of space. This scenario isn't science fiction. It's a very real possibility, rooted in the deep physics of our planet. What would happen if Earth's magnetic field, our planet's invisible shield, suddenly collapsed? This isn't just a question for geophysicists or astronomers. The answer would touch every single life on this planet, fundamentally altering our technology, our biology, and our very civilization. It forces us to confront our vulnerability, to understand that our existence depends on a force we can neither see nor touch. It's a force generated thousands of kilometers beneath our feet, a cosmic guardian we have always taken for granted. In this exploration, we will embark on a journey from the molten heart of our world to the farthest reaches of our atmosphere and beyond. We will peel back the layers of our planet to understand how this shield is created and why it is so crucial for life. We will witness the immediate, cascading consequences of its failure, a worldwide technological blackout, a sky filled with radiation. This is a guided tour through a hypothetical yet plausible future. It is a story of science, survival, and the profound choices humanity would face when our planet loses its most fundamental defense against the cosmos. So, what is this magnetic field, and why is it so important? Think of it as Earth's planetary force field. It's an immense, invisible bubble of magnetic energy that surrounds our world, stretching tens of thousands of kilometers out into space. This field is not static. It's a dynamic, life-sustaining structure generated by the swirling, superheated liquid iron that makes up our planet's outer core. This colossal planetary engine, known as the geodynamo, has been running for billions of years. It's the reason a compass needle points north. And it's the silent protector that has allowed complex life to flourish on Earth's surface, safe from the harsh realities of space. The primary role of this magnetic shield, or magnetosphere, is to deflect a constant high-energy stream of charged particles spewing from the sun. This stream is called the solar wind. Without the magnetosphere, this relentless barrage of radiation would slam directly into our atmosphere. Over time, it would strip our world of its air and water, molecule by molecule, leaving behind a barren, lifeless rock much like Mars. The magnetic field acts as a gatekeeper, diverting the vast majority of these dangerous particles safely around our planet, creating a protected pocket of space where life can thrive. It is, quite literally, the barrier between a living world and a dead one. This shield is not just about protecting our atmosphere in the long run. It also guards our biology. The particles it deflects are a form of high-energy radiation that is harmful to living organisms, capable of damaging DNA, and increasing the risk of diseases like cancer. The magnetosphere, along with our atmosphere, works to keep surface radiation levels low enough for us to exist. Furthermore, Our modern technology-dependent civilization is exquisitely vulnerable to the very solar particles our field deflects. Intense solar storms, if they were to hit Earth undefended, could overload power grids, destroy satellites, and cripple global communications in an instant. Therefore, the question of what happens if this field disappears is one of the most profound what-ifs we can ask. It's a scenario that would unravel the fabric of our world on every level. The consequences would not be a single, dramatic event, but a cascade of failures and long-term changes that would challenge our ability to survive. We would be exposed, vulnerable to the raw power of our own star. To truly understand the stakes, we must first journey to the center of the Earth and discover how this incredible, life-giving shield is born, and how we know that one day it might falter. Table of Contents. Part 2, Act 1, How the Magnetic Field Works, about 4 sections. 1. The engine at the center of the world. 2. A planet-sized bar magnet. 3. The ever-shifting field. 4. The solar wind and the magnetosphere. To understand our planetary shield, we must begin our journey deep beneath our feet. Thousands of kilometers below the ground we walk on, past the solid crust, the viscous mantle, lies the heart of our world, the core. This core is divided into 2 parts. At the very center is a solid ball of iron and nickel, squeezed by immense pressure into a solid state despite being hotter than the surface of the sun. Surrounding that solid inner core is the true source of our magnetic power, a vast, turbulent ocean of liquid metal, primarily molten iron. This outer core is a realm of unimaginable heat and pressure, a place where metal flows like water in a perpetually churning, chaotic dance. This swirling ocean of liquid iron is the engine of our planet. It is not a calm sea. It is a dynamic, convecting system. Hotter, less dense iron from near the solid inner core rises. Cooler, denser iron from the outer edges sinks back down. This constant circulation, known as convection, creates immense, slow-moving currents within the liquid metal. But this movement alone is not enough to generate a magnetic field. The other crucial ingredient is Earth's rotation. As our planet spins on its axis, it drags this flowing liquid iron along with it, twisting these rising and falling currents into colossal, spiraling columns. This complex twisting motion is called the Coriolis effect. It is the combination of these 2 forces, convection and rotation, that turns our planet's core into a gigantic electrical generator. The movement of the molten iron, an excellent electrical conductor, generates powerful electrical currents. Any moving electrical current creates a magnetic field. In the core, these currents are so vast and organized by spin, they produce a magnetic field that extends far out into space. This self-sustaining process is known as the geodynamo. It is one of the most elegant and powerful phenomena in our solar system. The geodynamo is not just a theory. It's a living process that has shaped our world for billions of years. It's a planetary engine that has been running almost as long as Earth, protecting the fragile surface from the harshness of space. Without this churning, electrically charged ocean of iron deep within our world, life would never have emerged. Our atmosphere would have been blasted away, our oceans boiled off into space. The engine at the center of the world is not just a geological curiosity, it is the silent, beating heart that keeps our planet alive and habitable. A constant source of power we have only recently begun to truly understand. The result of this incredible process deep within the core is a magnetic field that, from a distance, looks surprisingly simple. To a first approximation, Earth's magnetic field resembles that of a giant bar magnet, the kind you might have used in a science class. This imaginary magnet is tilted slightly, by about 11 degrees relative to our planet's rotational axis. This is why the magnetic North Pole is not in the exact same location as the geographic North Pole. The field has a North Pole and a South Pole. Invisible lines of magnetic force loop out from the South Pole and curve around to enter the North Pole. These magnetic field lines are what guide a compass. A compass needle is itself a small magnet. It naturally aligns with the local direction of these invisible lines. Near the equator, the field lines run roughly parallel to the surface, so a compass needle lies flat. Closer to the magnetic poles, the lines curve steeply downward. A dip needle will point almost straight down near the magnetic North Pole. The field's strength is not uniform. It is strongest near the poles, weakest near the equator. The bar magnet image is useful, but the true process is far more complex and messy. The geodynamo is chaotic and turbulent. The magnetic field is not perfectly smooth or stable. It has lumps, bumps, weak spots. One major weak spot is the South Atlantic anomaly, stretching from South America to Southern Africa, where the field is unusually weak. There, the inner Van Allen radiation belt, a band of trapped energetic particles, dips closer to the surface, exposing orbiting satellites to higher radiation. This anomaly shows our field is not a static, perfect shield. These observable facts give scientists a window into the core. By mapping field strength and direction globally, researchers build models of fluid flow deep inside Earth. We measure this with ground-based observatories and with dedicated satellites like ESA's SWARM mission. These precise measurements give more than a snapshot. They let us track change over time. What they show is our planetary shield is in constant and perhaps accelerating flux. Section 3. The ever-shifting field. One of the most startling discoveries of modern geology is that Earth's magnetic field is not permanent. It changes. It wanders. It can even completely flip over. By studying the geologic record, scientists dig up the past. Magnetic minerals locked into ancient volcanic rock record the field. Use geological cross-section image here. Scientists have built a timeline stretching back hundreds of millions of years. When lava cools and solidifies, tiny magnetic grains align with the Earth's field at that moment. Like countless tiny compass needles frozen in time, this creates a permanent record of orientation. This field of study is called paleomagnetism. It has revealed a dramatic history. The poles have reversed hundreds of times. North has become south. South has become north. Reversals are irregular and unpredictable. Sometimes they last millions of years. Other times just tens of thousands. The last full reversal was about 780,000 years ago. We may be overdue. During a reversal, the main dipole field weakens significantly. The field becomes more complex and messy. Multiple north and south poles can pop up worldwide. Eventually, the field reorganizes, usually opposite to before. This isn't only ancient. We see changes now. Since the 1830s, the field's strength has weakened about 10%. The magnetic North Pole has been moving. For over a century, it drifted slowly. In recent decades, its pace has accelerated dramatically, from about 15 kilometers per year to over 55 kilometers per year. It recently crossed the prime meridian. It moved away from the Canadian Arctic and is heading toward Siberia. This rapid wandering signals a restless dynamo beneath our feet. Some scientists speculate we may be entering an early reversal stage. It's not certain. The field might weaken and then recover without flipping. But the possibility is real. What would extreme magnetic weakness mean for us? The transition period could last several thousand years. That would be a time of maximum vulnerability. The shield that blocks dangerous cosmic and solar radiation would be at its lowest ebb. That prospect carries profound implications for all life on the surface. Section 4. The solar wind and the magnetosphere. To understand why a weakened field is so dangerous, we need to look outwards, towards our star. The sun is not a gentle, steady lamp. It is a raging nuclear furnace. It constantly spews a stream of charged particles into space. This stream is made of protons and electrons. It is called the solar wind. It travels at incredible speeds, typically around 400 kilometers per second or over 1,000,000 miles per hour. This is the constant background state of space weather, a relentless high-energy flow carrying the sun's magnetic field. Without protection, any planet in its path would be scoured and eroded. This is where our magnetic field performs its most critical function. As the solar wind approaches Earth, it first encounters our planet's magnetic field. The collision creates a boundary. The magnetosphere. The magnetosphere is the region where Earth's magnetic field dominates. It acts like a ship's bow plowing through water, creating a shockwave, the bow shock, and diverting the bulk of the solar wind around the planet. It forms a protective teardrop-shaped cavity with Earth inside. The side facing the sun is compressed. On the night side, the field is stretched into a long tail, called the magnetotail, which extends for millions of kilometers. However, this shield is not impenetrable. Some high-energy particles become trapped in the magnetosphere, forming two donut-shaped zones of intense radiation, the Van Allen belts. These belts encircle Earth and hold particles that spiral along magnetic field lines. Furthermore, during powerful solar events like coronal mass ejections, the solar wind can become a raging storm. Those storms can compress the magnetosphere dramatically and funnel enormous energy and particles into the upper atmosphere, especially near the poles where field lines dip down. This creates the beautiful and intense auroras. This brings us to the crucial point we foreshadowed earlier. What happens when this shield weakens? A weaker field means a smaller, less robust magnetosphere. It would be more easily compressed by the solar wind, allowing the boundary to move closer to Earth. The Van Allen belts could dip lower, and more radiation could penetrate deeper into our atmosphere, not just at the poles, but across the entire globe. The delicate balance that protects our technology, our atmosphere, and our very DNA would begin to break down. The stage would be set for the first, immediate consequences of a world losing its invisible guardian. Section 1. The sky on fire. The very first sign our magnetic shield has failed would be a spectacular, terrifying, global light show. The aurora, usually confined to polar regions, would no longer be a rare treat near the Arctic or Antarctic. Instead, they would erupt across the entire planet. As the magnetosphere collapses, the solar wind, that constant stream of charged particles from the sun, would no longer be deflected. It would pour directly into our upper atmosphere at all latitudes. The sky becomes the front line, the point of impact between cosmic energy and our fragile blanket of air. These global auroras would be unlike anything we've ever witnessed. Imagine looking up from a tropical beach in the Maldives or the bustling streets of Lagos and seeing the sky ablaze with curtains of green, red, violet. These colors come from solar particles, mostly electrons and protons, colliding with atoms of oxygen and nitrogen. The energy from those collisions excites atmospheric gases, making them glow. High-altitude oxygen produces eerie red light. Lower-altitude oxygen glows brilliant green. Nitrogen adds hues of blue and deep pink. Beautiful, but deeply ominous. Visible proof our planet is exposed to the full force of the sun. The lights would fluctuate wildly with the changing solar wind. During a solar storm or a coronal mass ejection, the entire sky, day and night, could become a seething, shimmering canvas. This isn't a gentle glow, it's a high-energy bombardment. The upper atmosphere would be superheated and ionized on an unprecedented scale, triggering the first of many cascading failures that would bring our modern world to a standstill. Atmospheric chaos would also change the sky's chemistry. Energetic particles would start breaking apart molecules in the upper atmosphere, particularly ozone. The ozone layer that shields us from UV would begin to erode. The chemical reactions start immediately, even if biological impacts at ground level take time. The sky would not just be filled with light, it would be filled with the byproducts of its own destruction, initiated by the loss of the invisible shield that once kept these energies at bay. While the sky puts on its terrifying display, our high-tech civilization would begin to crumble. The first victims of the collapsing magnetic field would be the thousands of satellites orbiting our planet. These marvels of engineering, on which we depend for communication, navigation, weather forecasting, scientific research. They are designed to operate within the relative safety of the magnetosphere. Without that shield, they would be flying naked through a storm of high-energy solar and cosmic radiation. The South Atlantic anomaly, a weak spot in the field that already poses a threat to satellites, would essentially expand to cover the entire globe, but far worse. The delicate electronics aboard these satellites would be bombarded by particles that cause phantom commands, memory corruption, and sensor damage. This is known as a single-event upset. More powerful particles could cause permanent damage, frying circuits and rendering the satellite useless. Solar panels, which power the satellites, would degrade at an astonishing rate, shortening their operational lives from years to mere weeks or even days. Within a very short period, our orbital infrastructure would start to fail en masse. GPS signals would become unreliable before vanishing entirely. Satellite television, long-distance phone calls, and international internet traffic routed through space would cease to function. Our window on the world would go dark. This orbital catastrophe is directly analogous to what happens during an extreme solar storm, but on a permanent and more devastating scale. The Carrington event of 1859, the most powerful geomagnetic storm on record, occurred when our magnetic field was at full strength. It still induced electrical currents so powerful that telegraph systems caught fire and operators received electric shocks. In a world without a magnetic field, the effects of even a minor solar flare would be amplified 1,000-fold. The constant stream of solar particles would induce powerful, uncontrolled electrical currents in any long conductor on Earth's surface. This includes the vast networks of our power grids. Transformers, the crucial nodes of our electrical distribution systems, would be pushed past their breaking points by these geomagnetically induced currents. They would overheat, melt, and explode. The result would not be a localized blackout, but a continental-scale grid collapse. Restoring power would not be a matter of flipping a few breakers. It would require replacing thousands of massive custom-built transformers, a manufacturing and logistical challenge that takes years even under normal circumstances. Our electrified world would be plunged into darkness, not for hours or days, but potentially for years. The collapse of the power grid would represent the single greatest blow to the functioning of modern society. Without electricity, the world we know simply ceases to exist. The immediate aftermath would be confusion and growing panic. Homes and cities would go dark. But the loss of light is the least of the problems. Water pumps stop, sewage and waste removal stop, sanitation systems fail within days. Waterborne diseases like cholera and dysentery would skyrocket. Refrigeration and supply chains collapse. Food distribution grinds to a halt. Communication rewinds. Worse than the 19th century. Satellites fail and the power grid is down. No internet, no television, no telephones. Even radio is disrupted. Global auroras and atmospheric chaos slam the ionosphere. Radio propagation becomes turbulent and unreliable. Communities are isolated, cut off from news and government. The world becomes disconnected islands of information. Financial markets and digital records are wiped out. The global economy vaporizes. Manufacturing stops. Transport fails. Commerce breaks down everywhere. The web of global dependencies unravels with terrifying speed. This is a fundamental threat to survival for most people. Cities rely on electricity, water, food, and information. They are artificial ecosystems that collapse without these inputs. A prolonged global blackout turns them into death traps. People are forced to evacuate. Mass migrations. The struggle for basic resources begins. Clean water, edible food, physical security. Humanity is pushed into a new dark age, not from lack of knowledge, but lack of power. Long before the full societal collapse takes hold, another fundamental system we take for granted would fail: our ability to navigate. For millennia, humanity has relied on the Earth's magnetic field to find its way across oceans and continents. The simple magnetic compass was a revolutionary technology that opened up the globe to exploration and trade. In a world without a stable magnetic field, this tool becomes useless. The needle would either spin randomly or drift aimlessly. This loss would have an immediate impact on all forms of transport not reliant on GPS, which would have already failed. Commercial airliners, which use magnetic compasses as a crucial backup system, would face immense challenges. While they have inertial navigation systems, these drift over time. Those systems require periodic correction from external sources like GPS or magnetic heading. Without them, long-haul flights, especially over oceans or vast, featureless terrain, would become incredibly hazardous. Ships at sea would be in an even more perilous position, reverting to the ancient and far less precise art of celestial navigation, provided the skies were clear. This sense, known as magnetoreception, is crucial for the epic migrations of sea turtles. Salmon, birds, monarch butterflies, they use the field's direction and inclination, the angle at which the field lines dip towards the surface. That acts as a natural GPS to guide them across thousands of miles to their breeding and feeding grounds. The collapse of the field would be a sensory catastrophe for these creatures. These animals would be lost. Migratory routes followed for millions of years would dissolve into confusion. Birds might fly in the wrong direction, exhausting themselves over open ocean. Sea turtles would be unable to find the specific beaches where they were born to lay their own eggs. Salmon would fail to locate their natal streams to spawn. This isn't just a tragedy for the individual animals, it would trigger a global ecological crisis. The sudden disruption of these migrations would cause populations to plummet, leading to collapses in food webs and devastating impacts on ecosystems that depend on the seasonal arrival of these species. As our technology fails and our cities go dark, a more insidious and silent threat begins to make itself known, With the magnetic shield gone, the Earth's surface is now directly exposed to a constant drizzle of high-energy particles from space. These are not just the solar wind particles, but also galactic cosmic rays, extremely energetic atomic nuclei originating from distant supernovae and other violent celestial events. Previously, the magnetosphere and our thick atmosphere worked in concert to protect us, absorbing or deflecting this radiation. Now, only the atmosphere remains, and it is not enough. The invisible rain of radiation begins to fall on every square inch of the planet, day and night. This bombardment would cause a significant increase in radiation levels at the ground. Estimates vary, but it's plausible that background radiation could increase by several orders of magnitude, reaching levels that are unsafe for long-term exposure. This isn't an instantaneous, lethal blast like one from a nuclear bomb, but a chronic, pervasive hazard. It would be like living in a world where a low-level radiological disaster is happening everywhere, all the time. People living at higher altitudes, where the atmospheric blanket is thinner, would be at the greatest risk. Denver, Mexico City, La Paz would become radiation hotspots, with exposure levels several times higher than at sea level. The consequences would not be limited to the ground. Air travel, which would already be perilous due to navigational failures, would become a serious health risk. At typical cruising altitudes of 30,000 to 40,000 feet, the atmospheric shielding is much weaker. A single long-haul flight could expose passengers and crew to a radiation dose equivalent to many years' worth of ground-level exposure under normal conditions. During a solar storm, the dose could be acute and immediately dangerous. The era of casual air travel would be over. The skies, once a highway for global commerce and tourism, would become a forbidden zone, a realm of high radiation that humans could only enter at great peril. This new radiological environment would force a fundamental change in human behavior. Staying outdoors for extended periods would become a calculated risk. The simple act of farming, construction, or even walking outside would contribute to a person's cumulative radiation dose. Society would be driven indoors, or even underground. New architecture would need to incorporate heavy shielding, using thick layers of earth, concrete, or lead to protect inhabitants from the constant cosmic ray shower. The world outside would become an alien and hostile place, not because of a change in temperature or weather, but because of an invisible poison falling from the sky. The scenario of a magnetic field collapse is a journey into one of our deepest vulnerabilities. A stark reminder that our complex civilization exists only by the grace of powerful planetary forces far beyond our control. The consequences: the technological blackout, the ecological unraveling, and the pervasive radiation paint a picture of a true apocalypse, a world thrown back into a dark age defined by a struggle for basic survival. It is a humbling thought experiment. revealing the fragility of the systems we depend on. Yet, as we stand at the end of this hypothetical timeline, the most crucial takeaway is not one of inescapable doom. The final, and perhaps most surprising reveal, is that a magnetic field collapse is not an instantaneous extinction event. It is a crisis that would be survivable, albeit at a terrible cost. The key difference between this scenario and, for instance, a massive asteroid impact is time. The geological record shows that magnetic field reversals are not instantaneous flips. They are slow, gradual processes that unfold over centuries, even millennia. The weakening of the field would be a measurable, trackable phenomenon, giving us decades or even centuries of warning. This is not a sudden catastrophe that strikes without notice. It is a slow-motion emergency. This warning is the most precious gift we could ask for, because it grants us the one thing that can overcome such a challenge: human agency. We would have time to observe, to understand, and to prepare for the coming changes. This is where the power of science becomes our ultimate shield. Our ability to monitor the geodynamo from space, to model its behavior with supercomputers, and to understand the physics of radiation shielding gives us the tools to mitigate the worst effects. Preparedness on a global scale, hardening our electrical grids, building satellite redundancies, developing radiation-proof data storage, and designing shielded habitats and indoor farms could transform the collapse from an extinction-level event into a manageable, albeit monumental, engineering and societal challenge. The cost would be astronomical, but it would be a price paid for the survival of our species and the preservation of knowledge and culture. Ultimately, the story of a world without its magnetic shield is not just a cautionary tale, it is an inspiring one. It underscores the incredible resilience of life and the profound power of foresight. Our planet's restless heart may one day falter, but our own ingenuity and collaborative spirit can rise to the occasion. By looking deep into the Earth's core and far out into the cosmos, we gain the wisdom to protect ourselves. Science gives us the ability to anticipate the future and, in doing so, gives us the power to change it. The invisible field that guards us is a wonder of nature, but our capacity to understand and adapt is the true force that will determine our destiny.